So I have an aggressive agenda, but it's, I have an hour and change. If we get through all of this, we do. If we don't, because we have good questions, everyone wins. But as time permits, we're going to learn how to spell GPU. We're going to do some simple GPU offloading examples, talk about programming models for when we get sick of doing things like writing CUDA memcopy, talk a little bit about libraries, maybe get to a little case study with molecular dynamics, and I'll pretend to give a conclusion. So one thing I will say up front is I work for Nvidia, which means I'm going to tend to use Nvidia and CUDA specific terms. I am going to try to call out some of the vocabulary for other vendors' GPUs like AMD and Intel's. I'm not here to speak the good gospel of Nvidia specifically, but I am going to slip into, again, Nvidia specific language. It's my fault, not yours. Cool. All right. What is a GPU? Why use it? How do you spell it? Just kidding. Let's talk about CPUs first. CPUs are designed for executing sequences of operations, which we call thread. It's designed to do it as quickly as possible with things like data caching and flow control in mind. And modern CPUs have, order 10 threads. It's not, this might be dating myself or maybe not others, but, I once had a 1-core Pentium 4 CPU, and folks who are older than me are rolling their eyes and thinking about how lucky I was. But this on the left of the slide is really meant to be a sketch, a schematic, but it's supposed to give you a rough idea that the computation logic or the green cores, it's part of it, but there's also a good amount of silicon logic for control flow, caching, things like that. A CPU, is running your computer's operating system. So it has to be good at doing that. And of course, lots of other things, scientific computation too, but it needs the logic to help you surf the web. Okay, now let's talk about actual GPUs. So GPUs are also designed for executing sequences of operations, again, called a thread, but it's, as quickly as possible, raw throughput in mind, and there's tens of thousands of threads going on. So again, on the left here, we have a sketch, a schematic, and I'll actually, hop to the next slide to show that. On the left, we have core logic, but also control flow, caches, things like that. On a GPU on the right, it's, compute, and there's like this control logic, and there's a cache and things like that. But that's sort of meant to give a very, schematicized idea of the different things going on. To go back to this very last point on the bottom right, a GPU is not running your computer's operating system. It's not designed to, and that's okay. That's why we're here. So this slide in some regards is from 10 years ago originally, where GPU offloading wasn't as huge of a thing. At this point, a lot of applications do support GPU offloading. But historically, this is kind of what the porting process looked like. You had some application code running fully on the CPU, and you wanted to go faster. So you kind of windowed out this little bit of very compute-intensive functionality, and you said, I'm going to get this on the GPU, and the stuff that's hard to parallelize, hard to run concurrently on accelerated hardware like a GPU, we'll keep it on the CPU as long as that matters. There are plenty of good candidates for GPU work out there. So algorithms with very clear, very massive parallelism. You have tens of thousands of cores. What types of things will scale meaningfully to tens of thousands of cores? So obviously there's vector addition, matrix multiplications, very large or small fast Fourier transforms. And then there, as part of what you're learning a lot about this week probably, is there are scientific calculations with lots of natural or hierarchical levels of parallelism. And this comes across a whole breadth of domains. mean, obviously, you're all here. You're probably thinking about molecular dynamics. So there's applications like Amber, GROMACS, LAMMPS, NAMD for molecular dynamics, all with a lot of great support for GPU offloading, exposing parallelism at the level of atoms and the neighbors of atoms as makes sense. There's lattice quantum chromodynamics, the study of the strong nuclear force. That's my original background. That discretized work on a 4-dimensional grid. So each grid site can map to a thread. Computational fluid dynamics, an example of that is the software out of NASA, Fun3D, that actually does a lot of different things. I'm not even going to begin to list everything, but you can consider, if I'm simulating a fluid, maybe each atom or some domain of a fluid could map onto a thread. And there's lots more. So I've kind of alluded to, what are GPU strengths and considerations? What's the real work it's good for? Kind of first and foremost, GPUs are floating point monster machines. So if you're doing floating precision or single precision computation on an Nvidia A100, this is for the 80 gigabyte version, but this is also true for the 40 byte giga version that's in the Perlmutter supercomputer at NERSC that Rule's going to talk about later. That's cranking out 19.5 teraflops at maximum. That's a marketing number. Almost everything is a marketing number these days, but you can still get a really good percentage of that. Don't tell my employer I said that's a marketing number. So, a teraflop is, what is that? Is that a trillion operations? No, that's a quadrillion operations. It's a lot of operations per second. That's not your casual Pentium 4 or, vector machine or, I don't know, your Atari. Another key strength that GPUs have, though, is they are memory bandwidth beasts. So again, the same A100 GPU has 2 terabytes per second of memory bandwidth, which is due to very efficient, literally called high bandwidth memory, as opposed to GDDR memory that you'd see on CPUs. And I guess for context, to be pedantic, the 40 gigabyte versions on Perlmutter have 1.5 terabytes per second. Oh no, still really fast. What that means, though, is you really, GPUs, you got to do a lot of work on a GPU to keep up with memory bandwidth. And this is sort of the first way in which you need to think about GPU work a little differently. So, we're going to do some kindergarten division. And if you take this, 19.5 teraflops, divide it by this 2 terabytes per second, if you want to shift from writing an algorithm that's just bound by memory bandwidth to something that's actually on net doing more compute, that's almost 10 operations per byte. So what do I mean by that? I mean, so for example, FP32, a single precision floating point number, is 4 bytes. So for every one single precision number you load, you need to do 38 operations to not be bound by this ridiculously insane high bandwidth memory. In contrast with CPUs, I forget the rough number off the back of my hand, but it's historically order 1, might be a little bit more at this point, which is both a statement of, it's a ratio. CPUs may have a lower, teraflops, but also slightly lower memory bandwidth for cases where it's, again, fast DDR memory, but not HBM memory. So what this means is you have plenty of room to do computation. It may be faster to do otherwise expensive calculations than to use lookup tables. So a historical example could be, for the molecular dynamics folks, there's a potential known as the embedded atom method. And if you look at a lot of common implementations of it, it's implemented via lookup tables. If you go back to the original paper on the embedded atom method, you'll see that the lookup tables are really largely just sums of exponentials. And one thing I wanted to do in advance of this was actually do the comparison But one thing I always think about is maybe I should just code that up as the sum of exponentials and see what happens. And on the other hand, if you said on a CPU, like, oh, I have to sum a bunch of exponentials, you'll use a lookup table instead. So a good way to think about it is, memory is cheap. You can do a lot of compute, take advantage of it if that means you can save loading things from memory. I'm not even going to pretend to give a complete talk on this idea, but there's an idea called the roofline method. And it's a way to look at your algorithms, think about if they're memory bound or compute bound. And that's going to tell you like, oh, can I refactor my algorithm for a GPU in a way to better take advantage of all the compute capability you have? That may sound a little rambly. It's because I am not smart enough to describe the roofline method in good faith. So if you take one thing away from this, if you write one thing down, write down this paper, give it a read. It's great reading. Pour yourself a pot of coffee. Roofline, an insightful visual performance model for floating point programs and multi-core architectures. It's a great read. It's a great read if you're here, you'll probably find it a great read. So one last idea before I jump more into what it means to really offload something to a GPU and use different performance portable kind of approaches is something that's very common these days and has really been around for a while, is the idea of heterogeneous computing. So, earlier I presented this, like, okay, you have your CPU program. Now I'm going to put things on the GPU. That might be a waste of your CPU. A modern compute node, again, a Perlmutter node. So that's a nice little sketch on the left. It has a CPU. It has 4 GPUs. It's connected to an ultra powerful, ultra fast network. There's lots of work to do things. There's, it can be non-trivial, not always feasible, but there's scope to simultaneously run on the GPU, on the CPU, and also do communications on the network. A really good example of this comes up in biomolecular simulations. For those who've thought about those, where you have local work to do and you also have long-range forces to do, which you'll do in practice by going into Fourier space. And that's a lot of different stuff to do. You can do all the short-range stuff on the GPU and at the same time do the FFT and all the communications for it on the CPU and get better throughput. So that's sort of a really high-level overview of some parts of modern GPU programming, or taking advantage of the full system that isn't so much there if you were coming to this talk 5-10 years ago. All right, let's talk about a GPU. My favorite thing to do is to just add vectors together. All science, obviously, is just adding a bunch of vectors together. Said no one ever. But it is a really good example of GPU programming, of GPU offloading. Okay, so who's written a for loop? Awesome. Some of you have written a for loop. This is great. So the only thing I want to do with this for loop is, which I have this array, and I want to take each element and I want to say, for each element I in arrays A and B, add them together, store it into C. So I want to write a program that does that, and I'm using C++. I'm not using Python because I want to make my life hard. And I got to go through all of this. I have to, allocate an array, fill it with stuff, and then I write this for loop to sum everything together, and then I'm done. And that's a lot of boilerplate for a pretty simple line of code, but okay, that's pretty manageable boilerplate. Now, CPUs have been around for a long time, and at some point, someone decided, I want to make it simple to then run this across multiple cores. And someone came up with the idea of OpenMP. It's a very long-standing, simple way to expose multi-core CPU parallelism. Simple for simple things. It's simple for harder things like, okay, pour a pot of coffee, come back to me in a year. But what's nice is it's so-called pragma-based. So you take your exact line of code, this for loop kind of in the center, summing things, and you just like stick this nice little, hashtag, hash or hashtag #, again, generational, pragma OMP parallel 4, and then you're like, wham, your compiler handles all of the parallelism for you. And it's great. In theory, for a long enough array, things just run faster. So now let's move to the GPU and see why I'm going to talk about much simpler things soon enough. So a little bit of background, and this is NVIDIA-centric background, vocabulary and stuff like that, but I'm going to try to do some translation as appropriate. So the CUDA architecture, which I think stands for Compute Unified. Exactly, it's an acronym. It's called it. You'll call it CUDA. AMD has ROCm, or their HIP abstraction. Intel's really pushing One API and SYCL. I think those are kind of the big ones if you're looking at current and upcoming supercomputers in the U.S. And internationally. So what's the idea of CUDA? It's a way to expose GPU parallelism for general purpose computing, as opposed to the original days of GPUs where someone said, like, ooh, I can take this GPU shader program that can make a Ripley pattern on a surface and force that to do math for me. So on top of that, you have CUDA C++, which is based on industry standard C++. And that's a really key theme I'm going to come back to later on. There are a lot of things that are, again, CUDA-specific APIs, HIP-specific, SYCL-specific. One thing that's good to come back to is ultimately using as many standards as possible. And that's something that's going to come up later, also in the context of things NVIDIA is doing. But, for the time being, we're just going to think of it as a set of straightforward extensions to enable doing concurrent CPU and GPU, or as I said before, heterogeneous programming. And in theory, it has a straightforward set of APIs to do everything you need to do. We're going to talk about CUDA C++ for the next stretch. There's also Fortran bindings, and a really big, more recent push, and a really official push is actually in Python. I don't like Python, but that's because I'm curmudgeon-y and like curly brackets or end statements. But it seems to be a hot commodity these days, so you can do GPU programming there too. So what does it mean to move your code to the GPU? Well, you write a function. Everyone loves writing functions. And you stick this special keyword on it, underscore, underscore, global, underscore, underscore. And that tells your compiler, like, cool, device GPU function. And then your compiler, in the case of CUDA and the NVIDIA platform, it's called NVCC, which will process the device functions and then make the host compiler do the rest. For AMD, that's HIP Clang, if I remember correctly. And then I've lost track of what Intel calls their compiler, but I think their ICC is now also Clang or LLVM based. But almost all GPU compilers have this split compilation model. And when you want to launch a function, you have this special triple angle bracket. It's sometimes called triple chevron. I think chevron means angle bracket, but I don't know. It's a bunch of less than and greater than signs. And that tells your compiler, run this on the GPU, and you're good. Now, one thing I will say is, again, that's specific notation for Nvidia and AMD GPUs. If you're using CUDA or HIP, other vendors, other approaches, your mileage may vary. Cool. All right, so I want to run that on the GPU. So all I do is I stick addition in some global function called vec add, and I call it, and it does a sum, right? It's that easy. Not at all. So I've been talking a lot. I've realized, is anything, let me take a break. Let me breathe. Who's with me so far? Who's with me? Cool. Don't be ashamed. Don't be afraid. Who's a little bored and seen this before? This is a judgment-free zone, but it also lets me kind of get a thermometer of what's going on. Okay, cool. That means in theory I'm being helpful today, which is great for my ego. All right, so for a while I talked about this idea of memory management, or not memory management. I did a lot of talking about GPU memory. We have this great, really fast HBM memory. I talked about how CPUs have, generally GDDR memory. These are the types of things I should get straight at some point. And the key thing is, it's different physical hardware. I have my, so-called host or CPU. That's this on the bottom left. That's a really old CPU and some sticks of RAM. On the top right, you have, this is an older Nvidia GPU, our quote unquote Tesla series, which at this point is kind of more just our data center cards. So CPU memory, GPU memory, different things. So you have different pointers or references to memory locations. So there are device pointers that point to device code, and you generally don't touch it from the CPU, with exceptions that are becoming more and more prominent, more recently. And likewise, you have host pointers that point to CPU memory, and you're not accessing them from your GPU device. Again, with other special cases, we'll save our energy, breath, time, things like that. And then there's a simple API for handling device memory where CUDA malloc is allocating memory on the GPU, freeing it is freeing your allocated memory, and memcopy is copying. And this is similar to the old school C equivalents to allocate host memory. So all of a sudden, you're going to get the impression really fast that things are going to slow down in terms of how much code you have to write. So I went through all of this work allocating my host arrays and deleting them later. And now I have to allocate some device memory. Oh boy. And then I have to copy it to the device. So all I wanted to do was do C equals A plus B. But then I had to allocate these device pointers, and I have to copy A and B to the device before I can do anything. And then I do my addition on the GPU. And then I'm like, oh, got to copy this back to the host. So you call your copy, and then when you're done, you call your free, and then life goes on. Now, I should take a minute to do a little bit of a sidebar here to say that this is a very obviously contrived example. In reality, you're going to set up things on the host, hopefully do a lot of work on the GPU so you don't have to do all these copies all the time, and then copy back at the end. But one thing I'm sort of trying to motivate relative to the CPU code is so far it's like, this has been a nightmare. This is a mess. Who's sick of all these extra functions to copy things to a GPU? Y'all are, yeah. There we go. People are starting to come alive. I mean, I see this. I'm not going to lie. I had to look up these function names because I didn't have to look up the function names. I had to look up the arguments and the order of the arguments because no one wants to memorize this. I go on Google. I'm like, oh, basic GPU code, and I copy, paste it, and change things because this is a nightmare. But despite that, we're going to do a little bit of a review, go through a few more nightmares, and I'm going to tell you, like, for a lot of things, this was useless, and we're going to make programming on a GPU a little bit more easy. But, you know, GPU kernels, you write a function, you stick global on it, it's a GPU or device kernel. You have to go out of your way to allocate memory explicitly with a CUDA malloc and a CUDA free. You have to explicitly copy it between the host and device, or, you know, CPU and GPU memory. And we got to figure out how to actually write a GPU kernel and, like, do things with it. All right. Who's good so far? Cool. All right. For the folks who don't feel good so far, do you feel, are you sort of here? Or are you like, oh, I've had this class before, stop talking? This is purely a laugh-based question. All right, I see a lot of smiles, so I'm going to assume that people are either agreeing with me or are embarrassed that I'm saying these things. Okay, so let's go back to talking about the GPU. GPUs and blocks and threads, oh my. So when you launch work on a GPU, this isn't like a CPU where your work is just going on in your single main thread or, you know, distributed over multiple threads on your CPU. GPU work is launched across multiple threads in units called blocks. You know, again, this is CUDA specific terminology. You know, on AMD for HIP, it's work groups of threads. Cocos, which is a performance portability framework used for GPU offloading and lamps and a bunch of other things. It's called teams of threads. OpenACC, which is a, you know, pragma-based way to offload to GPUs, which I'll talk about later. It's called gangs of vectors. You know, I wish we could have, you know, in 2000 or something, gotten everyone from the past, present, and future to come together and agree on a set of terms, but that would be too nice. Now, one important thing when you want to do these big calculations is you want to think about and be aware of a sense of locality. So for, you know, a CPU cluster, you know, forget about GPUs. When you're running on a big CPU cluster, you know, you have your single node, and that has a really nice sense of locality. And if you want to spread work across multiple nodes, or even on a CPU across multiple threads, there's a sense of data locality, memory locality, a sense of the amount of time it takes to communicate. And threads within blocks running on a GPU have that same type of concept. So there are certain guarantees. You know, in this schematic on the left, each one of these rows, in reality, you know, they're rectangles on silicon, but each one of these metaphorical or schematic rows is something called a streaming multiprocessor, or an SM, that contains a bunch of CUDA cores that can be doing work. When you launch a chunk of work or a block of threads, all of them are on the same SM, which means, you know, they share caches for fast communication or like good reuse of data. They can explicitly synchronize, which is cool, and they can share data explicitly through sort of a scratch pad memory. So locality is great. And the nice thing is all of this is runtime. I'm going to give some examples where I'm going to bake in some numbers, but this really kind of gives a sense of generality. I can run a small problem or a big problem on a GPU, and I don't have to bake in these thread or block numbers, which is kind of analogous to, you know, I don't have to bake in an upper limit on my for loop. So because we needed more vocabulary, threads are grouped into something called a warp on NVIDIA GPUs. And this is a 32 that the hardware told you about, not one that you can set. On AMD, I'm 99% sure it's 64 threads in a wavefront, because, again, we needed a new name for something. I don't think what it is on Intel GPUs is public yet, but maybe I'm wrong. I don't know. I wear green things. So, but presumably similar concept. Warps are the units in which threads are launched. So all threads in a warp, in principle, execute together and simultaneously in in one GPU cycle. And the idea here is called SIMT, or single instruction multiple thread. Some of you may have heard the phrase SIMD from CPU programming. Yes, no, raise your hand. Some of you, okay. So SIMD, we'll talk about SIMD first. It's, you have a single instruction that's executing on multiple data within a single thread. So in the context of CPUs, you may have heard something called SSC instructions or AVX. You may have seen Intel market AVX 15 to you. You may have heard AMD talking about how they're finally getting AVX 512. So those are the types of things going on there. On a GPU, it's not, one thread is processing multiple bits of data simultaneously. It's each thread in a warp is launching the same exact instruction. And that's some of what gives a GPU a certain sense of its efficiency. A CPU is doing all this control logic for each piece of data, or like little chunk of data for a vector instruction. I lost my train of thought. For each piece of data in a vector instruction, that's all part of the control flow. And if each core on a CPU is doing that, each one has its own separate data flow managing that. On a GPU with a SIMT model, you have your warp, 32 threads, pieces of data. It's like, bam, all same thread executing everything together. That's efficient. So how do we take advantage of this? So, threads and blocks get enumerated, in some order that gets launched on a GPU. And in CUDA, there's special built-in keywords that you can use to access and index your different memory locations. So in this vector add function, that's how you get this, this I, your vector index. So there's these built-in block index.x and thread index.x. Was that a question or just me echoing or something? Oh, okay. I hope enjoying warmer LA weather relative to the snow and rain we got here on Tuesday. So we have these random thread indices. How do we use these to access elements in the array? And this is sort of a way to think about it. So how many folks have dealt with two-dimensional for loops or nested for loops? Okay, cool. For loops, they're great. It's kind of the similar idea here, except there's a more meaningful hardware analogy here. So if we consider some setup where we have, 8 threads in each block, don't do that. 8 is less than 32, but just for conversation's sake, we have blocks that don't execute in order if you follow the CUDA programming guide, where each block has its own index, and within each thread or within each block, there are 8 threads you can index over. So with that, you can flatten your index, flatten your array, flatten your index as a function of the thread index and the block index to get a way to index into your 1D array. Or you can use another keyword to avoid baking in a size. And I'll make a sidebar here that, it's thread index.x. You can do 2-dimensional and 3-dimensional launches, and you do that if you have some degree of hierarchical parallelism. So some type of natural, I'll go back to molecular dynamics. Some type of example of if I wanted to parallelize over atoms and neighbors of atoms, maybe my .x will be atom number and my .y could be neighbor index of that atom as sort of a way to think about where multidimensional parallelism could come in. So cool. We can actually do this. We can write our function. We can get our index I as a function of the thread index and the block index and the block size. So maybe we can do real work now. So we can modify our code, put in a number of threads per block, and then we can modify this triple chevron structure, this vector add, to launch, n divided by the number of threads in a block blocks with 512 blocks each. And cool, we're doing work. And then as a last comment, not all problems are powers of 2, unfortunately, or fortunately, depending on how much interesting work you want to do. So you can add a little extra cheat bounds onto your function to say, okay, maybe I have 15 pieces of data. My GPU is going to launch, in that original schematic, 8 times 2 threads, whether I want it to or not. So I want to lop off that 16th thread that doesn't have data. So I put in a little if statement. And then everything can just go in at runtime. Okay, so we'll do a little bit of review and pause for questions if there are any, and then kind of move along. So, work is launched in blocks of threads and in units of warps. Thread index.x and block index.x can be flattened into a linear index. So I can finally do my for loop. So I think I just spent 25 minutes going through a bunch of boilerplate to literally write this for loop on a GPU. And it's important boilerplate because we did have to talk about the hardware. We did talk about data motion, but it was a lot to just add 2 vectors together. I talked about this review. We're good. So now let's talk about doing things more sanely, or different GPU programming models. So this is kind of the obligatory, I didn't want to make a slide covering different things, so I stole an Nvidia marketing slide. But I'll go into the ways this does, kind of map onto all different architectures, vendors, things like that. There's, in a broad sense, kind of 3 hierarchical ways that you can be targeting GPUs without pulling your hair out. The rightmost one is specializing, writing very specific CUDA code. I'll get into how there's, pragma-based codes that are going to look really similar to that really simple OpenMP parallelism example. And then there's a lot of work going into, I just want to be able to write in vanilla, boring C++ or Fortran or Python and not care about any of this. So, I can avoid all of this hoopla with writing separate functions and these weird thread index keywords that I have to, remember, again, copy paste every single time I want to write a new piece of code. I can do directives. One thing I'm not going to be able to spend anywhere near as much time as I want to on is general performance portable frameworks. A really good example of this is Cocos, originally out of Sandia, but now it's kind of fueled by a multi-lab, et cetera, consortium without industry people making decisions, which I'm biased as an industry person, but as having a science background, it's nice that it's separate. And then, again, being able to write things in just native C++. And depending on your programming background, that bottom line down there, that transform statement may still look a little scary, but it's a lot better than all of that data motion stuff I had to write down in the first place. At least I think so. So one option is something called OpenACC, which was originally developed by, so it is a formal consortium of multiple different groups, originally implemented in something called the PGI compiler, which is the Portland group something that Nvidia bought at some point. But it is still an open standard that other folks contribute to. And in theory, it's really easy. With OpenMP, I had my Pragma OMP parallel loop above my for loop. And now it's Pragma ACC parallel loop. And then, okay, so I did that. That's cool. I still had to think about my data motion. So whether or not you like it, you generally do, for decent performance, do have to care about when am I copying things to the GPU, when am I copying them back from the GPU. So there's this little bit of extra, like, okay, I have to copy in this vector A and B, and I have to copy out this vector C, but I wasn't writing any verbose, CUDA mem copy, function call, CUDA mem copy. I just stuck this pragma on it and my life went on. And that's really nice that, I didn't have to go through 20 minutes of slides talking about CUDA APIs to get you running on the GPU. I could have just been like, all right, this is it with OpenMP. Here it is with OpenACC. Let's move on. So there also is an extension of OpenMP for CPUs, which is OpenMP target offload. I copy and pasted some code from Raul from NERSC, who's going to be giving a talk to y'all later today, which means he wrote good code that's much smarter than mine, and I didn't rip out some extra things that he includes because it's helpful for performance. So that's why this is a little bit more verbose. It doesn't have to be. But this does look, ignore some of the keywords, this does look pretty similar to an OpenACC Pragma. It's still Pragma OMP. The target's like, all right, I'm offloading to a target, a device, a GPU. And otherwise, that's about it. Instead of copy in, copy out, I have to use these map keywords. So, okay, I'm still going to have to remember if I'm using OpenACC or OpenMP, and if I have to use copy in or map. But again, this is it. You're done. I didn't have to explicitly write a CUDA malloc. I didn't have to explicitly write a mem copy, anything like that. Just these relatively simple pragmas take care of everything for me. So the pie in the sky, though, is I don't want to have to write any of this stuff. I just want to take vanilla C++ code or Fortran code or Python code and then just have some way to specify, run this on the CPU, run this on the GPU, with some complexity, handle memory motion for me, and just like, let me write my code and go on with my life. So this is something that there's a lot of support we're working on in the Nvidia stack, but this is something that's also going to go, it is becoming part of the C++ standard, is not just an Nvidia thing. So you can write the same code wherever, and you can modify something on your command line when you compile, something Raul will be talking about later, and you can say, run this on the CPU. And then you change a single flag, you say, parallelize on the GPU instead of on multiple cores, otherwise the same, and the same exact code runs, which is great, which makes things, everyone's happy, everyone wins. So simplicity normally comes with a cost, which can be a concern. So there is, to give some background, there are some standard C++ benchmarks to quantify these different things. How do different kind of standard building blocks perform as a function of these different backends when you're running on the GPU? So some very simple standard things are, there's copying, C equals A. And again, so that's just C++. There's no for loop with a pragma ACC parallel for or pragma OMP target, etc. It's just I wrote down a copy. there's multiply. I rescale the vector by a scalar. There's add, which is everyone's favorite code based on how much I've talked about it, I'm sure. There's the triad, which is a fuse multiply addition. And then there's dot products reductions. And that's the basis of, to a degree, that's the basis of all linear algebra. And like 80% of scientific computing, and the other 20% is perturbation theory on top of that. And what's cool is, besides some back-end work, because nothing's perfect on the first try, all these different, this approach is as good as any other. So I'm showing, this lower left graph is some performance numbers for all these different options on the x-axis, copy, multiply, add, triad, and dot product. The y-axis is, what's my bandwidth I'm sustaining. This is all bandwidth bound code. And you'll see, the left blue code or bar is OpenACC. Orange is like torturing yourself with all of that stuff to write CUDA code. Gray is OpenMP, target device offload. And then the yellow and the blue, the rightmost blue, STD is, standard C++ with a couple different ways of launching the work. And what you'll see, with the exception of the dot product, which can get trickier because there's a reduction, it doesn't matter. So for relatively simple operations, you could say, like, I'm going to write all this boilerplate, or you can say, I'm going to write a one-liner or, four-liner. So that's something nice. If you do want to look into this, I definitely recommend looking at the work, the basis of these Babel stream benchmarks, because it can be a way to look at how these different little things are implemented. The link's down there. If I remember correctly, this is being recorded and uploaded. I think I should be able to share these slides too. So I think that may just come down to how well some parts of it were implemented, in the sense that these benchmarks are really good, but maybe not perfect, which I know is sort of a cop-out answer. But I assume someone made this plot and has fixed the code since then, because in theory, all of these should have the same performance as a bandwidth bound. But good question. I know you're awake. I wasn't worried, but now I know for sure. So I'm going to give a quick sidebar, a shout out to Cocos, because I really love using it. So as I said, Cocos it's not an Nvidia product. It's not an AMD product. It's, the Cocos C++ performance, portability, blah, 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 writing modern C++ in a hardware agnostic way. This is the truest marketing sounding statement I've ever read in my life. This one actually really isn't garbage. It has the various abstractions you can think about. Parallel for loops, reductions, scans, supports CPU offload, GPU offload, memory abstractions. It was used for a Gordon Bell finalist in 2021 that myself and Aiden were on. Danny, I forget if you were on it, and if I'm embarrassing you incorrectly, I'm sorry. I can't keep track of these things. One reason why I do want to make an extra special pitch for Cocos, though, is to some degree the dream for Cocos is to become obsolete. Cocos is a staging ground for various C++ ideas for data parallelism, device offload, things like that, that are directly going into C++ 17, especially C++ 20, 23, and so on. So there's kind of this nice hope that you're going to write some Cocos code, some data parallel Cocos code, and then at some point you'll be able to rip parts of it out and just use a standard parallel C++ call. So that's kind of a way for me to say that I've thrown so many different ways to write parallel code at everyone so far. And it's like, oi, which one do I learn? And my personal take is, standard, non-vendor specific standard C++ is going to be the sane way of the future to write code, with some, with asterisks that I'll get to, obviously. And if you want to learn something that's going to be a really good on-ramp for that, if you're going to start there today, Cocos is a really good thing to learn, and they have really good tutorials. But that's sort of my sort of soapbox. I've taken off my Nvidia hat, I've put on my scientific computing hat. Cocos is pretty sweet. All right, now I'm putting my Nvidia hat back on. All of these different things, I'll step back and say, multiple vendors, multiple different companies all have stacks like this with various level of maturity in different bits, but they're all working towards making a great stack. Different companies are eventually interested in standard C++ and Fortran, or, this is the leftmost box, OpenMP, maybe OpenACC, and their own analogs of CUDA. There are compilers. I'm going to have a little sidebar about libraries. They're going to care about network stacks, which I alluded to a little bit, and Raul will tell you a little bit more about during his talks. And there's profiling tools. But everyone kind of has, different companies have their own nice stacks to write raw code, write this pragma-based code, standard C++ code. The Nvidia HPC SDK mouthful acronym, etc., is our own. Check it out. Raul will probably, I think the code samples he's going to be showing will directly take advantage of that on Perlmutter with things that carry over. Okay, so I promised a sidebar on libraries. Here's your sidebar. Take advantage of optimized libraries. This is not a GPU-specific slide. There are many standard kernels in scientific computing that come up everywhere, vector additions, like dense linear algebra, fast Fourier transforms, random number generation. Many open source communities and vendors put a lot of effort into highly optimized implementations. Like, all of you are smart. You were accepted into this program. I am smart. I am talking to all of you at this prestigious program. It's nothing personal. You or I just aren't going to do as good of a job at this. It's just like, put your ego in a box. Like, yeah, you can write a good matrix multiply. Someone else has done it. They've done it better than you, probably, and me. Take advantage of this amazing work of others. If you are afraid of vendor lock-in, cool, I get it. There are open source communities who are doing similar things. As I'll get to in a hot second, NVIDIA's trying to make drop-in replacements to make this easy for you to just target open source APIs. But regardless of the way you do it, again, y'all are great. I'm great. A lot of people are better at this specific thing, and take advantage of their time. NVIDIA does have a bunch of libraries that map onto other standard libraries. There's cuBLAS, which is, you stick CUDA in front of BLAS for basic linear algebra subroutines, for dense vector, and matrix operations. There's cuSparse, which is standard sparse matrix operations. cuTensors are a thing for tensor contractions that might come up in deep learning, but also quantum computing. Quantum computing has a lot of tensor contractions in it, for those of you excited about that latest buzzword. And all other sorts of things. And we do have drop-in replacements, so you can actually just look up standard BLAS routines and write them, and then get them running on NVIDIA GPUs. But a sidebar I will say is, again, if you're afraid of lock-in or using really old Fortran BLAS APIs, There is work towards a C++ native version of BLAS, which I think is going to start hitting, I think in C++ 26. I don't think any of it's going into C++ 23. So that's cool. That's, again, this is reemphasizing standard C++ is a good part of the future. There's interfaces to LAPACK for sparse, or dense linear solves, and also FFTs. And the last cool thing, and then I swear I'm done with NVIDIA specific stuff, I promise, is good libraries for distributed, dense solves, symmetric eigensolvers, different factorizations, and then distributed FFTs. So one cool thing I'll say, though, is, yes, we're developing our own. Why are we developing our own? And it's because there's a community out there, there's open source software that you can use that's still really good to do this. You can find distributed FFT code. You can find existing code for distributed symmetric eigensolvers. The one here, ELPA, I forget what it stands for, but it comes up in diagonalizing structure functions for molecules or something like that. And this is the type of stuff that's collaborative and based on what the community needs. And in some regards, this is me saying, when you see a slide that says, look at this cool thing a vendor has, it's because the community did something too. So you can look at the slide and you can say to yourself, I need a sparse, I need an eigensolver. I'm going to go check out ELPA and, ELPA, I don't know how it's said, and do my own thing. Okay, let me get off my libraries soapbox and kind of dig back into the heart of a lot of what I've been saying, which is, why would I write one of those disgusting raw kernels? And hopefully what you've taken away from me so far is just don't. If you don't have to, don't. It's terrible. If you can use a library call, do it. Again, we're all smart. Other people are smarter. Take advantage of their work. Specialize in what you specialize in. Take advantage of simple things, fragment-based offloading. As these ISO C++ and also Fortran, Python features are developed, take advantage of those. Keep things simple and standard. For even more complicated concepts, take NVIDIA hat off, put scientific computing hat on. Cocos does an incredible job and is actively developed. I do make a joke about taking my NVIDIA hat off, but we also endorse it too, because it is a great piece of software or a great programming model. Sometimes you are going to need that raw pedal to the metal to get that last 1, 5, 10% of performance. Aiden pointed out some discrepancies between some of the different streaming vector operations across different backends. Vector operations are relatively simple things, but there are going to be some cases where for a more complicated hierarchical algorithm, scientific algorithm, you're going to have a hard time in the short term, medium term, getting all of that raw performance out. And on one hand, when that happens, find someone and complain. Find me and complain about it. Tell us to do a better job. But sometimes you're going to want that cutting edge hardware feature, and that's where you're going to write a raw CUDA kernel. Or someone's going to hand you a piece of software and tell you to write something, and you're going to see that it's written in raw CUDA kernels, so you're going to copy, paste, and change things as you need to, and never write something from scratch. So we have 13 minutes left. I have a kind of hack and slash discussion of applying some of these ideas to molecular dynamics. But before I talk about that briefly, I want to just kind of stop, pretend for a second that we're actually at the end of my talk. Ask me questions, politely yell at me, give me feedback. How's everyone feeling about GPUs? Are you excited? Are you scared? I can't blame you. They scare me too.
excited.
All right, I see someone with your hand up in the back. What's up?
Yeah. So this is very good, and the CUDA benchmark is great for alpha. I guess alpha was partly started. I mean, the GPU part was partly started by Nvidia, right? And so.
Oh, cool.
There's some Nvidia people on there.
Oh, what was that last bit? Sorry, your voice just cut out for me.
Yeah. But I think the bigger issue with the libraries thing is that that CUDAs came pretty late. Right? Otherwise, we wouldn't have actually written something like alpha for GPUs. So the problem is that eigensolvers for a very long time did not scale across nodes, which is a serious limitation of GPU architectures.
Mm-hmm.
That maybe changed in 2021, right? But I guess it took the community library to change that.
Mm-hmm.
Yeah.
Yeah. No, and that's a fair and valid point.
So it's great that Nvidia did something now, but we wouldn't have had to do that work if we would have had a working architecture.
Yeah. And that, so I guess this is more of a, it's the unfortunate tension sometimes between,
this was not a matter
of knowing the future. Yeah.
Of the application developers having to do that work because it wasn't there and it needed to be there.
And obviously, it's easy to say now, like, yeah, it would have been cool if we got on that sooner. Some of this is credence to there being a really strong open science community with good things you can leverage. And that's also some of why, like, obviously I had my NVIDIA-centric things because of the powers that be, but I try to talk and think a lot about open standards, open resources. Yeah, it would have been great. And I would have found it great if NVIDIA solved that problem sooner as someone who's dealt with sparse eigensolvers before. But what's cool is there is ELPA out there for a broader community of scientists, whether or not they're running on NVIDIA GPUs. And that's cool. So that's the flip side. That's me taking my vendor hat off on saying that it's great when vendors get involved and they get involved early, but sometimes that can get in the way of the broader community having things at first. Take that as you will. Don't tell my employer.
A quick question, Evan, about the heterogeneous aspects of the machine. So is there a way to express that once you launch your thing on the GPU,
mm-hmm.
you might want to keep doing something else on the CPU in the meantime while the GPU is crunching? And in the simple ways to express things, it seems to be synchronous, right? You start your kernel, you wait that it's done, then you come back on the CPU, and then something else happens. But is there a way to express that multiple things are happening at the same time in a simple way?
Yeah, so by default, I didn't really get into this, but by default, that kernel launch was technically asynchronous. But it launched in a so-called default stream, and then it waited on, it was sort of contrived, but it waited on the copy afterwards. So by default, you could have just written that line of code as is, and it would have started cruising along on the GPU, and you could have immediately started writing CPU code, and you could have synchronized later. There is also, even within just launching GPU kernels, there's an idea called, you can create separate streams, and you can launch work on to launch kernels and also a lot of, but not every API on a separate stream. And with that, you get guarantees of ordering within the stream, but the driver can make a bunch of decisions on what order to launch things in. And once you've launched everything, again, the CPU is free to do whatever you want. Like a couple exceptions of blocking operations here and there, but it is nice. I will say, though, as a Cocos person, there are some catches where some Cocos GPU launches will be inherently blocking, and I'm working on helping them out with that. There's various technical performance reasons why that's going on, which we can talk about for sanity's sake offline. Was that a question in the back or a stretch?
Yeah, I have a CUDA Python question, if that's okay.
Sure. I may not be very good at answering, but I will try or point at resources.
It's a big picture question. For people familiar with CUDA C and C++, is there anything big to look out for using CUDA Python? Like, are things like memory allocation, race conditions, like usual multi-threading programming stuff? Is it a lot different moving to Python, or?
So I think there's a few answers to that. So one is, I think we are working on native API, native mappings for the different malloc, et cetera, APIs. We are working on just native offloading in for loops. If you're familiar with NumPy in Python, there's not perfect drop-in, but pretty good drop-in called CuPy, which kind of has all the same analogous things that will let you create a GPU native vector and just do work on that. And I assume it has APIs to copy things from the host just for kind of reasonableness reasons, but I've never written it myself.
Thanks.
Ian, you had a question?
I have. What's going to happen in 5 years? Are we going to have to do another massive rewrite of Snap, or are things going to be more stable?
I'm running out of ideas for Snap.
Or any code? I mean, it was a huge shift to go from the CPU platforms to the GPU platforms, and are things going to be more stable from now on, or are they going to continue to be more huge shifts?
That's a tough open-ended question. Kind of, I mean, for kind of the standard virtue of if I knew what 5 years from now was going to look like, I'd be buying certain stock and not others. I think that a lot of the design patterns and new ways we're thinking about exposing concurrency and parallelism are going to remain stable for the next 5 years. I mean, CPU to GPU programming requires a lot of different ways to think about how you expose parallelism. But one nice benefit of that shift is that way of thinking about it still does map nicely onto the CPU. So I don't know if, at least for a lot of standard scientific computing algorithms, I don't know if there's going to be some new paradigm that kind of breaks that. But I don't know.
For example,
do
you think this flop to byte, memory bandwidth to flop ratio is going to change again, or is it going to stay roughly about this number of 38 that you cited?
I think that's going to stay kind of a similar order of magnitude. There's, it may go up, it may go down in future architectures, but it's sort of a statement of, how many what's the size of a floating point transistor? How fast can you get HBM memory and things like that? But famous last words about fundamental research and then scale out and things like that. The one thing I will say is I don't think quantum computing is going to solve all of our problems. But I guess it'll be good for factoring integers. I've got, yep. All right, well, in that case, thank you everyone for listening. Thank you for the questions. Again, thank the organizers for inviting me. For those who are going to be back or around for the longer program, I'm going to be giving a talk, another talk like 2 months from now, and I'll be there in person. So we can talk about whatever, and Aiden, we can talk about Snap in person too.
Well, let's thank everyone for
Thank you, everyone.
and we look forward to seeing you in a couple of months for the workshop. Thank you.
It's gonna be fun. Bye all.